Darwin Gödel Machine. Open-ended evolution of self-improving agents. Abstract. Most of today's AI systems are constrained by human-designed, fixed architectures and cannot autonomously and continuously improve themselves. The scientific method, on the other hand, provides a cumulative and open-ended system where each innovation builds upon previous artifacts, enabling future discoveries. There is growing hope that the current manual process of advancing AI could itself be automated. If done safely, such automation would accelerate AI development and allow us to reap its benefits much sooner. This prospect raises the question of how AI systems can endlessly improve themselves while getting better at solving relevant problems. Previous approaches, such as meta-learning, provide a tool set for automating the discovery of novel algorithms, but are limited by the human design of a suitable search space and first-order improvements. The Gödel Machine 116, on the other hand, introduced a theoretical approach to a self-improving AI capable of modifying itself in a provably beneficial manner. Unfortunately, this original formulation is in practice impossible to create due to the inability to prove the impact of most self-modifications. To address this limitation, we propose the Darwin Gödel Machine, DGM, a novel self-improving system that iteratively modifies its own code, thereby also improving its ability to modify its own codebase, and empirically validates each change using coding benchmarks. In this paper, the DGM aims to optimize the design of coding agents, powered by frozen foundation models, which enable the ability to read, write, and execute code via tool use. Inspired by biological evolution and open-endedness research, the DGM maintains an archive of generated coding agents. It then samples from this archive and tries to create a new, interesting, improved version of the sampled agent. This open-ended exploration forms a growing tree of diverse, high-quality agents and allows the parallel exploration of many different paths through the search space. Empirically, the DGM automatically improves its coding capabilities, e.g., better code editing tools, long context window management, peer review mechanisms, producing performance increases on SWE-bench from 20.0% to 50.0%, and on Polyglot from 14.2% to 30.7%. Furthermore, the DGM significantly outperforms baselines without self-improvement or open-ended exploration. All experiments were done with safety precautions, e.g., sandboxing, human oversight. Overall, the DGM represents a significant step towards self-improving AI, capable of gathering its own stepping stones along a path that unfolds into endless innovation. All code is open-sourced at https://github.com/genesity/DGM. Introduction. Scientific progress is cumulative and open-ended, with each breakthrough standing on the shoulders of countless prior insights. In the same way, our most advanced AI systems are built upon a long lineage of innovations. For instance, transformers, the backbone of current large language models, LLMs, did not emerge in isolation but were built upon years of past innovations, such as recurrent neural networks and attention mechanisms. However, most of today's AI systems remain bound by fixed, human-designed architectures that learn within predefined boundaries, without the capacity to autonomously rewrite their own source code to self-improve. As a result, each advancement in AI development still leans heavily on human interventions, tethering the pace of progress. This paper investigates the intriguing possibility of safely automating the search for ever-better AI. One can imagine an AI system that, like scientific discovery itself, becomes an engine of its own advancement, building upon its past, recursively improving and propelling itself toward more advanced capabilities. Schmidhuber presented a class of mathematically rigorous, self-referential, self-improving problem solvers. It relies on formal proofs to justify code rewrites, ensuring that any self-modification is provably beneficial. However, in practice and without restrictive assumptions about the system, it is impossible to formally prove whether a modification to an AI system will be beneficial. For example, While it may seem that an LLM-based coding agent would benefit from access to more tools, e.g., code search, test runners, the actual impact depends heavily on the model's training and task context. E.g., a testing tool that is optimized for one setup may confuse the agent when working with others. Instead of requiring formal proofs, we empirically validate self-modifications against a benchmark, allowing the system to improve and explore based on observed results. This approach mirrors biological evolution, where mutations and adaptations are not verified in advance, but are produced, trialed, and then selected via natural selection. We also take inspiration from Darwinian evolution and investigate the effectiveness of maintaining a library of previously discovered agents to serve as stepping stones for future generations. We propose the Darwin Gödel Machine, DGM, a self-referential, self-improving system that writes and modifies its own code to become a better coding agent. Each self-modification requires the DGM to edit its own code base. We use Python, which is Turing complete, giving the DGM the potential to build any computable machine. Our framework envisions agents that can rewrite their own training scripts, including training a new foundation model. However, we do not show that in this paper, as training FMs is computationally intensive and would introduce substantial additional complexity, which we leave as future work. Instead, this paper focuses on improving the design of coding agents with frozen pre-trained FMs, e.g., tool use, workflows. The DGM alternates between self-modification and evaluation phases. During the self-modification phase, selected coding agents from the archive generate modified versions of themselves. During the evaluation phase, each modified agent is tested on a coding benchmark, estimating the agent's coding capabilities and then added to the archive. By improving its own capabilities through this loop, the DGM becomes better at both solving coding tasks and making future self-improvements. A key assumption is that an increase in performance on coding benchmarks indicates better coding capabilities and hence better ability to self-modify and self-improve. Furthermore, the DGM maintains an archive of generated coding agents, initialized with only one agent, and continuously accumulates all generated variants over time. To support continual self-improvement, the DGM draws inspiration from open-endedness research, accumulating diverse stepping stones, i.e., interesting yet suboptimal solutions or features that may enable future breakthroughs. This open-ended exploration encourages the discovery of novel and potentially useful self-modifications beyond immediate performance gains. We present results on two coding benchmarks, SWE-bench and Polyglot. The DGM automatically improves itself from 20.0% to 50.0% on SWE-bench, and from 14.2% to 30.7% on Polyglot. We show that self-improvement enables continued progress, as the DGM outperforms the baseline, where the same initial agent is repeatedly used to modify and generate new agents without self-improvement. We also show that open-ended exploration and keeping an archive of all previously generated agents lead to the discovery of better coding agents. The DGM outperforms the baseline of not having open-ended exploration, i.e., a baseline without the accumulation of an archive of interestingly different stepping stones, where the coding agent always builds off the most recent version of itself. Overall, the DGM represents a step toward AI systems that can build upon their own prior innovations and improve recursively. We consider and discuss safety aspects extensively, including sandboxing and traceability of self-modifications, to ensure responsible experimentation. By advancing the possibility of safe, self-referential, self-improving models, the DGM moves us closer to AI that not only learns but evolves in an open-ended, self-accelerating trajectory, much like science itself. Open-endedness. A grand challenge for driving unbounded innovation is designing open-ended AI systems that continuously generate novel and learnable artifacts. Building on this, Hughes et al. Characterized open-endedness as a system's capacity to generate sequences of artifacts that are both novel and learnable from an observer's perspective. A central difficulty lies in structuring and exploring vast search spaces to consistently produce artifacts that are interesting to humans. Early efforts addressed this through quality diversity algorithms, goal-directed exploration methods, intrinsic motivation, or learning progress frameworks. More recently, large-scale foundation models have emerged as powerful proxies for human notions of interestingness and effective mutation operators to propose novel solutions in code. FMs can guide autotelic agents, model human preferences for quality and diversity, design reward functions, create simulated environments, drive ever-evolving multi-agent dynamics, search diverse ambulating robot morphologies, and search expansive solution spaces for benchmark or objective optimization. However, these approaches have yet to close the self-improvement loop, meaning improvements on downstream tasks do not translate into enhanced capabilities for self-modification or the acceleration of further innovations. We aim to mimic the acceleration of science and technology, where new tools and discoveries catalyze the creation of even more discoveries. Similarly, how can we emulate nature's arc of evolution, which bends not only toward complexity, but also an ever greater capacity to evolve? Meta-learning FM agents. Many FM-based agents are handcrafted. Some building blocks include prompt engineering, chain of thought, self-reflection, multi-agent debate, memory, temperature sampling, and retrieval augmented generation. The manual composition of these components limits the system's abilities to the ingenuity of its human designer. More recently, several meta-learning approaches have emerged that leverage FM to automatically optimize prompts and design agentic modules. The automated design of agentic systems, ADAS, iteratively generates downstream agents with a fixed meta-agent, evaluates them against a target benchmark, and incorporates feedback to refine subsequent generations. In contrast, the DGM is a single system that both solves downstream tasks, i.e., coding problems, and refines its own implementation, i.e., its code base, removing the need for a fixed, handcrafted meta-agent and enabling self-referential improvements. Self-improving AI. Early on, various researchers outlined theoretical and conceptual approaches to self-improvement. Some practical approaches to automated self-improvement include systems defined by neural network weight parameterizations. Metz et al. Developed a gradient-based optimizer that is self-referentially meta-trained using a variant of population-based training. Lang et al. Extended this approach to gradient-free learning. Silver et al. Used self-play to continuously evolve agents, achieving superhuman performance in challenging domains such as chess and Go. More closely related to the DGM are recent approaches that leverage FM-based agents for self-improvement. Zidikmoiyad use a meta-agent to generate downstream agents, updating the meta-agent based on the meta-utility derived from the generated solutions. In et al. Use a single system to both solve downstream tasks and recursively modify itself. However, the downstream tasks or the meta-utility do not always align with the capabilities required for self-improvement. In the DGM, improvement in downstream tasks directly reflects an increase in self-improvement ability, enabling the potential for self-accelerating progress. Most similar is concurrent work by Robians et al., which also has a single agent recursively solving coding problems and modifying its own codebase. The main difference between the DGM and Robians et al. Is that the DGM has an open-ended exploration loop, encouraging self-modifications beyond immediate performance gains and thus avoiding stagnation in suboptimal self-modifications. Darwin Gödel Machine. A Gödel machine is a theoretical construct describing an AI system capable of provably improving itself. In this work, we introduce the Darwin Gödel Machine, DGM, which aims to make this vision more practical. Unlike the original Gödel machine, which demands theoretical proof of improvement, the DGM instead relies on empirical validation. New versions must show performance gains through experimentation. However, depending solely on empirical evidence can trap the system in local optima within the vast space of computable algorithms. To mitigate this, the DGM maintains an archive of discovered solutions, supporting an open-ended search strategy instead of pursuing a single evolving solution. This process is inspired by Darwinian evolution, where innovation stems from selecting, modifying, and preserving interesting variants from a population of existing solutions. Self-referential self-improvement of coding agents. The DGM begins with a single coding agent, whose progress is measured through coding benchmarks. A coding agent in this context is a self-contained system built from a code repository and powered by frozen, pre-trained foundation models. These agents can read, write, and execute code. Prior studies have shown that such agents can enhance their performance through meta-level improvements in design, such as refining prompts, workflows, or tool usage, which are encoded within their own codebase. In our framework, self-improvement refers to the agent's ability to modify its own components. Since self-improvement is itself a coding task, demonstrating gains on benchmark tasks also indicates the agent's increased capacity to improve itself further. Population-based, open-ended exploration. Beginning with just one agent, the DGM constructs a growing archive of all agents it discovers. In each cycle, parent agents are selected to generate modified versions of themselves. Selection is influenced by each agent's benchmark performance and its capability to produce offspring with code editing functionality. A selected parent agent examines its previous benchmark logs, identifies the next feature to add, frames that as a new problem, and implements the feature within its own codebase, yielding a new coding agent. Each new agent is benchmarked to assess its performance. Only agents that compile successfully and preserve the ability to edit a codebase are retained in the archive. Others are discarded. This loop of selection, self-modification, and evaluation enables continual expansion of the solution archive. Crucially, agents that may seem suboptimal at first can later become foundational stepping stones for significant future improvements. Unlike approaches that simply iterate on the most recent best-performing agent, this method avoids getting trapped in local optima. Currently, the processes that manage archive structure and parent selection are fixed and not subject to modification by the DGM itself, which remains an area for future research. Experiments. Section 4.1 outlines the experimental setup, including the initial coding agent used to initialize the DGM. We conduct experiments on two coding benchmarks, SWE-bench and Polyglot. Section 4.2. For each benchmark, the DGM is compared against two baselines, one without self-improvement and another without open-ended exploration. Section 4.3. Across all experiments, the DGM consistently outperforms both baselines, demonstrating that both self-improvement and open-ended exploration are crucial for sustained performance gains. Section 4.4. Additionally, we show that features discovered by the DGM transfer effectively across different large language models. Section 4.4. 4.1 Experiment Setup. The DGM begins with a single coding agent. This initial agent is based on a foundation model, FM, enhanced with tool use capabilities. The FM autonomously decides which action to take at each step, selecting from available tools. Initially, the agent has access to two tools, a bash tool for running bash commands, and an edit tool for viewing and modifying directories and entire files, Appendix A.1. The agent receives a single input prompt specifying the target repository's location, the problem statement, and the repository's testing framework, Appendix A.1. The DGM runs for 80 iterations, generating one new agent per iteration, with 2 iterations running in parallel for SWE-bench and 4 for Polyglot, Appendix A.2. During self-modification, coding agents use Claude 3.5 Sonnet, new, for both benchmarks. During benchmark evaluation, Claude 3.5 Sonnet, new, powers the SWE-bench agents, while O3 Mini is used for Polyglot. For Point 2 benchmarks, SWE-bench and Polyglot are coding benchmarks designed to evaluate how effectively AI agents can solve coding tasks autonomously. Given a code repository and a task instruction, the agent is expected to modify the repository to fulfill the task requirements. Both benchmarks require the agent to navigate the codebase, understand interactions among functions across multiple files, and detect subtle errors in complex code. SWE-bench focuses exclusively on Python tasks, while Polyglot covers multiple programming languages. Another distinction is that SWE-bench tasks often require edits across multiple files, whereas Polyglot tasks primarily involve implementing solutions from scratch in a single file, though the agent still examines other files to understand the broader context, resulting in fewer file edits overall. These two benchmarks test different aspects of coding ability, allowing us to validate the DGM's effectiveness across a range of coding challenges. SWE-bench. To avoid wasting computational resources on unsolvable tasks, we use SWE-bench verified, a filtered subset of SWE-bench curated by human annotators to ensure that every task is solvable. Throughout this paper, the term SWE-bench refers specifically to this verified subset. Polyglot contains tasks in multiple programming languages such as C++, Rust, and Python. Compared to SWE-bench, which is widely used and likely included in foundation models training data, Polyglot is more niche and less likely to be part of the model's post-training data. Additionally, Polyglot is primarily used by the developers of Aider for evaluation. This presents an opportunity to compare automatically designed agents with a well-established community coding agent that has been continuously developed and tested against Polyglot over the course of a year by human developers. Moreover, Polyglot tests the DGM's ability to generalize across several programming languages beyond just Python. We follow a similar evaluation setup to the Polyglot leaderboard, with one important difference. While the leaderboard reports pass at 2 performance, where the agent can view feedback from ground truth tests once, we use a stricter pass at 1 setting, where the agent never sees the results of ground truth tests. Due to the high computational cost of evaluating on full benchmarks, we adopt a staged evaluation strategy to estimate the coding agent's performance. Generally, we evaluate the agent on more tasks as confidence in its strength increases. First, each coding agent is tested on 10 tasks to verify basic code-based editing capabilities. Only agents that maintain this ability can proceed to solve downstream tasks or perform further self-modifications. Agents that pass this initial stage are then evaluated on a larger set of 50 tasks. For SWE-bench, these tasks come from a representative mini-sample designed to reflect the full benchmark. For Polyglot, the tasks are selected as a random subset of the full benchmark. Because the foundation models are inherently stochastic, performance results can vary. Therefore, smaller subset evaluations are used to estimate general effectiveness and to identify the top-performing candidates. For SWE-bench, if a coding agent achieves over 40% success, a heuristic chosen based on the noise observed in preliminary runs, on the 60-task subset and ranks among the top 2 performers in the archive, it is then evaluated on an expanded set of 200 tasks, the initial 60 plus an additional 140. To more accurately measure its true coding ability. For Polyglot, if a coding agent surpasses 40% success on the 10-task subset, it proceeds to evaluation on a larger 50-task subset. 4.3 baselines. To isolate and evaluate the contribution of the DGM's core components, we compare the DGM against 2 baselines: DGM without self-improvement and DGM without open-ended exploration. The version without self-improvement replicates the approach where the meta-agent responsible for modifying the coding agents remains fixed as the initial agent throughout the experiment. This baseline helps assess the role of iterative self-improvement in accelerating the evolution of better coding agents. The version without open-ended exploration removes the archive and always self-modifies the latest stored version of itself. If a coding agent self-modifies to the point where it loses the basic functionality required to edit a codebase, it can no longer modify itself or solve any coding task. Therefore, this baseline retains the latest version that still maintains basic codebase editing functionality. This allows us to evaluate the impact of having an archive and the known benefits of open-ended exploration in guiding the agent's evolution. Besides these learned baselines, we compare the DGM against handcrafted, open-source solutions. For SWE-bench, we use the state-of-the-art open-source solution that has been independently verified by the benchmark team. For Polyglot, we use a representative agent designed to support multiple programming languages and large codebase editing. For a fair comparison, we measure the percentage of solved tasks on the same benchmark subsets used to evaluate the DGM. These results are shown as dotted horizontal lines in Figure 2. Figure 2. Self-improvement and open-ended exploration enable the DGM to continue making progress and improve its performance. The DGM automatically discovers increasingly better coding agents and performs better on both left SWE-bench and right Polyglot. It outperforms baselines that lack either self-improvement or open-ended exploration, showing that both components are essential for continual self-improvement. These scores come from evaluations on the benchmark subsets detailed in Section 4.2. After 80 iterations of the DGM, the coding agent's performance increases from 20.0% to 50.0% on SWE-bench, and from 14.0% to 38.0% on Polyglot, Figure 2. Since the DGM is evaluated on only 50 tasks in the Polyglot experiment setup, Section 4.2, we additionally evaluate both the initial agent and the best DGM-discovered agent on the full Polyglot benchmark to more accurately estimate the improvement. On the full Polyglot benchmark, the DGM improves the coding agent from 14.2% to 30.7%. This shows that the DGM can automatically self-improve to create a better coding agent. Moreover, the performance of the best DGM-discovered agent is comparable to that of Figure 3. The DGM automatically self-improves to become a better coding agent. Left, archive of coding agents generated during the DGM run on SWE-bench. Each node represents a coding agent, with node 0 corresponding to the initial agent. Node color indicates performance on SWE-bench, percentage of solved tasks, while border color reflects the number of tasks for which the agent was evaluated. Edges show which agents self-modified to produce the offsprings. Many paths to innovation traverse lower-performing nodes, and key innovations, like Node 24, lead to an explosion of innovations built on top of them. Both properties underscore the benefits of open-ended search. Right, progress plot of the DGM on SWE-bench. The light blue line shows the average score of all agents possessing basic codebase editing functionality. The blue line tracks the best score achieved by any agent in the archive at each iteration. The dark line shows the lineage of the final best discovered agent and its precursor nodes, which includes 2 performance dips. This illustrates the benefits of open-ended search, which explores a diverse set of interesting stepping stones instead of focusing only on branching off the best solution found so far. The performance of the DGM-discovered agent is comparable to the checked, open-source, human-designed SOTA on SWE-bench, Figure 2. On Polyglot, although the DGM starts with an initial agent whose performance is lower than that of Aider, it discovers an agent that far surpasses Aider, Figure 2. The DGM-discovered agents are comparable to or outperform handcrafted agents on both benchmarks. While the SOTA SWE-bench agent and Aider were painstakingly shaped by human efforts, the DGM hints at a future in which such ingenuity is automated, evolving through self-referential cycles of continuous self-improvements. The DGM automatically improves both the tools and the workflow of how foundation models are utilized, Figure 3. For example, the DGM enhanced the edit tool to allow more granular file viewing by lines and more precise file editing by string replacement instead of always viewing or replacing the entire file. Workflow improvements include making multiple attempts to solve a task and using another foundation model to evaluate and select the best solution. Other workflow improvements include considering previous attempts when generating subsequent ones. Appendix C.1 and Appendix C.2 show all modifications leading up to the final best discovered agents on SWE-bench and Polyglot respectively. Because open-ended exploration allows branching from any agent in the archive with non-zero probability, the DGM can get out of deceptive dips or peaks in performance. For example, at iterations 4 and 56 of the experiment on SWE-bench, although the agent's score temporarily fell below that of its parent, the DGM was still able to explore innovations along that path and create a new agent that outperformed all of its predecessors, Figure 3. Furthermore, open-ended exploration allows different implementations of the same target functionality to be attempted. For example, while the goal is to provide finer-grained editing tools, the specific implementation of this feature can vary greatly and hence lead to very different performance. Appendix D. The DGM can explore multiple implementations to find the most suitable one and avoid getting trapped in a suboptimal one. The DGM outperforms both baselines, DGM without self-improvement and DGM without open-ended exploration, on both benchmarks, Figure 2. In the case of DGM without self-improvement, where the meta-agent responsible for modifying coding agents remains fixed, early gains occur but quickly plateau. For DGM without open-ended exploration, only the most recent agent is retained. Thus, a poorly performing self-modification can make future improvements more difficult. To test the generality of the improvements from the DGM, we evaluated both the initial agent, Section 4.1, and the best agent discovered during the DGM run, Figure 2, using different foundation models than those originally employed. Figure 4. Transfer between models and tasks. The enhanced performance of DGM-discovered agents transfers effectively across different foundation models and task domains. For SWE-bench, the DGM was initially run using Claude 3.5 Sonnet, new. We then replaced the foundation model with Claude 3.7 Sonnet, or O3, Mini, and evaluated performance on 200 tasks, Figure 4, left. Using O3 Mini, the initial agent achieved 23% success, while the DGM-discovered agent reached 33%. With Claude 3.7 Sonnet, the initial agent scored 19%, and the DGM-discovered agent achieved 59.5%. For Polyglot, where the DGM was run with O3 Mini, we replaced the foundation model with Claude 3.5 Sonnet, new, or Claude 3.7 Sonnet, and evaluated on the full benchmark, Figure 4 middle. Using Claude 3.5 Sonnet, new, the initial agent reached 32%, and the DGM-discovered agent 33.3%. With Claude 3.7 Sonnet, the initial agent achieved 35.6%, and the DGM-discovered agent 36.8%. These results suggest that the improvements discovered by the DGM generalize well across different foundation models, rather than being tightly coupled to the specific model used during training. To evaluate transfer across programming languages, we train a version of the DGM exclusively on Python tasks for Polyglot, and then tested the discovered agent on tasks in other languages such as Rust, C++, and Go, Figure 4, right. While focusing on Python tasks slightly boosted performance on Python-specific tasks, it reduced performance on non-Python tasks compared to training on all languages. Nevertheless, after transfer to unseen languages, the agent performed comparably to the version trained on all languages and substantially outperformed both the initial agent and the ADER baseline. These findings demonstrate the robustness of the DGM's improvements, showing they do not overfit to a particular programming language. Safety discussion. Systems capable of self-improvement, such as the DGM, represent a step toward more autonomous AI development, aligning with long-standing goals in the field of making capable AI that can benefit humanity. 2071 87 115. However, this capability introduces unique safety considerations stemming from the system's ability to autonomously modify its own code. Modifications optimized solely for benchmark performance might inadvertently introduce vulnerabilities or behaviors misaligned with human intentions, even if they improve the target metric 12. In particular, if evaluation benchmarks do not fully capture all desired agent properties, e.g., safety and robustness. The self-improvement loop could amplify misalignment over successive generations. Iterative self-modification could also lead to increasingly complex and uninterpretable internal logic, hindering human understanding, oversight, and control. 6, 37, 44, 120. Recognizing these challenges, the current implementation and experimental setup of the DGM incorporates several safeguards. All agent execution and self-modification processes are conducted within isolated sandboxed environments, limiting their ability to affect the host system, and thereby mitigating the risk of unintended actions. Each execution within the sandbox is subjected to a strict time limit, reducing the risk of resource exhaustion or unbounded behavior. The self-improvement process is currently confined to the well-defined domain of enhancing performance on specific coding benchmarks by modifying the agent's own Python codebase, thus limiting the scope of potential modifications. Additionally, we actively monitor agent performance and code changes, with the DGM archive providing a traceable lineage of modifications for review. At this stage, we have found no evidence of harmful or malicious behavior in the generated agents, and the self-modifications have been primarily focused on improving coding capabilities. Conversely, a significant potential benefit of the self-improvement paradigm is that it could, in principle, be directed toward enhancing safety and interpretability themselves. We conduct a preliminary investigation into how the DGM can be deployed in AI safety settings to develop countermeasures for FM hallucination, Appendix F. Just as the DGM learns to improve its coding capabilities, it could potentially discover and integrate better internal safeguards or modify itself for greater transparency, e.g., incorporating principles akin to constitutional AI. If such properties were included in its evaluation criteria, 109. This suggests a promising, albeit challenging, pathway in which self-improvement becomes a tool for building more trustworthy AI systems. Additional research could also explore weaving constitutional AI in from the start, though the challenge will be incentivizing the system to retain these directives. An option worth exploring is to create an unmodifiable part of the system to be able to evaluate and halt the rest. The DGM demonstrates the potential of self-improving AI while still operating within safe research boundaries due to the current limitations of frontier FMs and effective mitigations like sandboxing. We include this safety discussion proactively to raise awareness about the emerging prospect of self-improving AI systems and their associated safety implications, particularly as these systems inevitably become more capable. Accordingly, we advocate for continued investigation into the safe and beneficial evolution of AI-generating algorithms, 20, and self-improving systems. Conclusion and limitations. We introduced the Darwin Gödel Machine, DGM, the first self-improving system powered by FMs with open-ended exploration, where progress on its evaluation benchmarks can directly translate into better self-improvement capabilities. We demonstrate the automatic discovery of better tools and FM systems, resulting in better performance on two benchmarks, SWE-bench and Polyglot. Through self-improvement and open-ended exploration, the DGM shows a continuous increase in performance, bringing us one step closer to self-accelerating, self-improving AI systems. We demonstrate that the DGM can autonomously achieve performance on par with openly available solutions. However, it still falls short of closed-source SOTA SWE-bench solutions. An open question is whether running the DGM for longer would continue to yield performance gains and eventually surpass closed-source solutions. These closed-source solutions often rely on elaborately handcrafted techniques developed by teams of highly skilled experts. Since FMs have yet to match the capabilities of such experts, e.g., in reasoning, the DGM currently requires extensive compute to discover improvements. A single run of the DGM on SWE-bench, as presented in Section 4, takes about 2 weeks and incurs significant API costs, Appendix B.1. We hypothesize that further progress will require more efficient use of computational resources and the development of better reasoning skills. Since this version of the DGM is mainly powered by FMs, it is inherently limited by the capabilities of the underlying FM. Hence, an exciting future direction is to extend self-modification beyond just prompts or FM workflows, to include more computationally intensive methods, such as rewriting its own training script to update the FM itself. While this version of the DGM focuses on coding, AI systems are increasingly applied across a wide range of domains, e.g., computer vision, creative writing. Another promising extension is to develop self-improving AI systems capable of enhancing themselves beyond just the coding domain. A key assumption in this work is that coding benchmarks are a good reflection of the agent's ability to self-improve, since the self-modification task requires the agent to modify its own codebase. However, one could envision an alternative approach that co-evolves the target task distribution, thereby removing the constraint of self-improvement being tied to a single objective, as in true open-ended processes. As discussed in Section 5, we must also continue to keep safety front and center as we explore this powerful technology. In conclusion, the DGM represents a significant step toward the automation of AI development through self-improving systems capable of editing their own codebase. While current limitations in compute and reasoning constrain its full potential, continued advances in FMs and infrastructure may unlock more powerful and general-purpose self-improvements, provided that the safety concerns are carefully navigated. Section 5. The future of self-improving AI systems and AI-generating algorithms, 20, holds immense promise to open-endedly evolve AI, continually rewriting or retraining itself in pursuit of greater capabilities aligned with human values. Acknowledgements and disclosure of funding. This research was supported by the Vector Institute, the Canada SFAR AI Chairs Program, a grant from Schmidt Futures, and CERT Discovery Grant, and a generous donation from Raphael Kosman. Resources used in preparing this research were provided, in part by the Province of Ontario, the Government of Canada through SFAR, and companies sponsoring the Vector Institute. https://vectorinstitute.ai/partnerships/current-partners. Any opinions, findings, and conclusions or recommendations expressed in this material are those of the authors and do not necessarily reflect the views of the sponsors. We also thank Aaron Arna, Ben Norman, Cedric Colas, and Sham Sadakaran for insightful discussions and feedback.